Hey guys, Mr. Patterson here with our video for IBAAHL. We're going to be taking a look at Chapter 27 in the Hayes and Harris book. We're only going to be doing the first half of Chapter 27 today, and then there'll be a separate video for the second half. But Chapter 27 is all about discrete random variables. Okay, so we're talking about what does it mean for a variable to be a random variable, and then specifically what is a discrete random variable. So as you see, there's lots of topics in this section. This first video is going to cover topics A through E. So we're going to talk about random variables in general, then specifically discrete probability distributions. Then we'll talk about expectation, another word for mean. Then we're going to talk about variance and standard deviation. And then finally, we're going to talk about these linear transformations that take the form of AX plus B. And then we'll have another video here to talk about the binomial discrete random variables later on. So let's take a look at the opening problem here. In this particular case, we are throwing, looks like darts or something like that, at a little bullseye here, and we're trying to win some prizes, like a carnival game, right? And there's different prizes we can win with associated probabilities underneath it, all right? So there's a couple questions we want to think about here, right? What's the sum of all the probabilities? Well, if we think about it, if these are all the possible values, then the sum of the probabilities should be 1, because that accounts for all possible outcomes. What is the most likely outcome? All right, so the most likely outcome is going to be the one that has the highest probability. So the most likely outcome would be $2 that you walk away with. The average result. Okay, so now we're talking a little bit more challenging of a concept. But basically, if we think of this as a weighted average, I could find that average as 0 times 0.5 plus 2 times 0.35, etc., on out there. And that would give me the average result. And then finally, what's a fair price for playing the game? So this idea of a fair price is basically if you charge exactly as much as you expect to gain in the game, then that's a fair game. Obviously, if you're running a carnival game, you're not going to run a fair game because a carnival game is meant for the runner of the game to make money. But that's generally what we're talking about here in this chapter. This is an example of a discrete random variable, right, where we don't know what the outcome is going to be. However, we can assign probabilities to those outcomes and then do some analysis of that scenario. But before we get too far into it, let's talk about probability in general, right? When we talk about probability in general, we're talking about the long run average, right? The long run average. So not what's going to happen the first couple times I observe something, but what happens if I observe something over and over and over and over again. That's what probability is. And when we talk about a chance event is anything that we don't know what the outcome is, right? The number of players on the football team who scored touchdown next match. We don't know exactly, right? But we have a pretty good idea. It's probably going to be, 0, 1, 2, 3, something like that. Not going to be too high of a number there. The time it'll take you to travel to school tomorrow. So it generally takes you maybe 10 minutes, but it could take you a little bit less or a little bit more, etc. So those are chance or random events. When we talk about random variables, we're talking about numbers used to describe the possible outcomes resulting from a random experiment. And since it's a variable, we generally call it X or Y or Z or any letter we really want to use there, but it is a variable that we denote with a letter here. Those types of random variables could be discrete or continuous. And as we'll go through here, discrete random variables are things that can be counted, right? So if you're talking about cricket, the number of wickets a bowler takes, or the number of light bulbs in a purchase of 50, number of defective light bulbs in a purchase of 50, excuse me. Those would be discrete because you can count them. A continuous random variable takes any value on a given interval. Those are things that could be measured. All right, so the heights of men. Maybe you're 50 centimeters, but maybe you're exactly 50.376 centimeters, right? Or any value between 50 and 250. The amount of water in a tank, right? Could be anywhere from 0 to whatever that particular tank holds. All right, so let's take a look at this example here. First one says, supermarket has 3 checkouts, A, B, and C. A government inspector checks the weighing scales for accuracy. The random variable X is the number of accurate weighing scales. Okay, so Question A says, list the possible outcomes and the corresponding values of x. Well, x could take any value from 0, 1, 2, or 3, because it's the number of accurate weighing scales. Maybe none of them weigh accurately. Maybe one does, two do, or all three do. When we say what's the value of x corresponding to there being exactly one scale, well, that's x equals 1. When we say at least 1, that's just going to be x is greater than or equal to 1. So we're just going to write it as an inequality. Taking a look at section B, now we're just going a little bit further, and we're going to talk about, okay, what if those probabilities aren't given to us, and we want to find those probabilities? Well, there's a couple of rules that we have to follow. First is that the probabilities have to be between 0 and 1 for all possible probabilities, and the sum of all the probabilities, that's this notation here, all the probabilities added up, they have to be 1. Okay? And when we talk about those probabilities, altogether, they make up a probability distribution. All right? We can represent these in a table as we see here with the x values and the probabilities associated. We can represent them in a column graph or in a spike graph. If we have a uniform discrete random variable, then we're basically thinking about the word uniform. That means everything's the same, right? So if we have a uniform discrete random variable, that's like rolling a die, right? Each one of those outcomes, 1 through 6, are equally likely, so that's a uniform random variable. When we talk about the mode and the median, those are two types of measures of center that we can find. The mode is just going to be the most frequently occurring, or the highest probability. The median is going to be the 50th percentile. In other words, if I count up all of the probabilities from the lowest value up until I get to the 50th percentile, that's where the median will be. So let's take a look at this example here. It says the magazine store recorded the number of magazines purchased by its customers in 1 week. 23 purchased 1, 38% purchased 2, etc. So let's just go through this. A says state the possible values of x. All right, no big deal. X could be anywhere from 1, 2, 3, 4, or 5. You might be thinking about why is there no 0? Well, are you a customer if you didn't buy anything? We'll see. All right. B says construct a probability table. Okay, so that just means I'm going to take those x values, 1, 2, 3, 4, and 5, and I'm going to put the probabilities underneath it. Now the probabilities should be a decimal, so I'm going to put it as 0.23, 0.38, 0.21, 0.13, and 0.05. All right. Check the probabilities. Are they all between 0 and 1? Do they add up to 1? Good. C says make a graph of the probability distribution. And it doesn't matter if I use a spike graph or a column graph. Just going to put those values there, 1, 2, 3, 4, and 5. Label that as x. Now my probabilities, I only need to get up to 0.4. That's my highest one there. So I'll count by 0.1. 0.1, 0.2, 0.3, 0.4. And then I'll just do a spike graph here. So we're going to go up. That's about 0.23, 0.38, and this is about there. You know what? I don't like that one. I'm going to do that one all over again. So 0.38, much better. 0.21, 0.13, and 0.05. All right. Then in D it says find the mode and the median. Okay, so the mode, if I just go to my table here, the highest probability is 0.38, so the mode is 2. The median, what I'm going to do is I'm going to count from left to right until I get to 0.5. So 0.23, not there yet. But if I add 0.23 and 0.38, now I've exceeded the 0.5 that I need to get the median. So that means the median is also going to be the value of 2 there. Excuse me. Now, not all the time are you going to have like a written explanation of the probability distribution. Sometimes you're going to have a function that defines those probabilities. So that's what's happening here in this example. So we are given this function, and they say, show that this is a probability mass function for these x values. So what I'm going to do is I'm going to make that table and just show that they add up to 1 and show that all the values are between 0 and 1. So if I plug 1 into the function here, I have 1 plus 1 over 34, so that's 2 over 34. And I'm going to keep it as a fraction so it's easier to add up. If I plug in 2, that's going to be 5 out of 34. If I plug in 3, that's going to be 10 out of 34. And if I plug in 4, that's going to be 16. Nope, that's going to be 17 out of 34, excuse me. And if I add all these up, hopefully I did my math right, they do in fact add up to 1. So I can say the sum of all of the probabilities is equal to 1, and all probabilities are between 0 and 1. All right. Looking at example 4, it says 2 marbles are randomly selected without replacement. That's a key there. There are 4 red and 2 blue, and they want to know, find the probability distribution of x if x is the number of reds. So what can x be? I could have 0 marbles that are red, 1 that's red, or 2 that are red. And now I just need the probability of each one of them. So if they're both not red, that means I had a blue one, which has a probability of 2/6, times the second one being also blue without replacement, so that probability changes to 1/5. But if I look at that there, that is going to give me 2 out of 30. So the probability of x equaling 0 is 2 out of 30. Now, that's if x equals 0. If x equals 1, well, that means one of them is red. So it could go red first, and then a blue, or it could possibly go blue first, and then a red. If I look at them, they both end up being the same fraction, right? 8 out of 30 and 8 out of 30. So together, they're going to make 16 out of 30. And if I have x equaling 2, that means they were both reds. That's 4 out of 6 times 3 out of 5, giving us the 12 out of 30. And double check here, that does add up to 30 out of 30, so we're good. The second part just has to make a graph, and you guys got that. I'm not going to worry about that right now. Expectation. So if you think about the word of expectation as what you expect, or the mean of the distribution, then this problem becomes a lot easier. So expected value, expectation, mean, they all mean the same thing. And if we're looking at this particular scenario here, assuming that all 4 of these regions are the same, we can find the expected value here just by saying, okay, I know that I have 5 plus 10 plus 15 plus 50 is 80, and each one of them are a quarter likely. So if I just divide that by 4, I get 20 as the expected points per spin. Notice I can't actually get a value of 20, but that doesn't change it being the expected value, because that's in the long run. Now, another way to look at expected value is, or E of x, is just to say, okay, that's just the sum of all the x times p's, all the sum of the x values times their probabilities. So if we take a look at this example, going back to example 2, if I wanted that expected value, E of x, I'm just going to do 1 times 0.23 plus 2 times 0.38 plus 3 times 0.21, etc. on out here. All right, and that's going to give me my expected value, whatever it ends up being. Okay. Fair game. So we talked about fair game before. We said if the expected value is 0, it's referred to as a fair game. So what would generally happen is they would give you a scenario where, okay, they would say, let's say we have a distribution kind of like we did in this spinning game, and they want to say, okay, how many spins should we charge, or how many points should we charge for this game? Well, if the expected value is 20, then we should charge 20 for the game to therefore give us a fair game. All right? And we could look at that with example 6 here, find the expected return. That's the same thing as the expected value, so we got that. If we are looking at question B, when it says expected gain, okay, so if you charge $5 to play the game, all you have to do to answer this question is find the expected value and then subtract 5 from it, because that's how much you're charging to play. And then when it says discuss whether you'd recommend playing the game, well, if your expected value, your expected gain is positive, then yeah, you should play it. But if its expected gain is negative, then no, you should not play it, right? But it doesn't mean that people make decisions that way, obviously. Casinos make millions and millions of dollars, or billions probably, yearly, just off the fact that people think that they can beat the system. Variance and standard deviation. Okay, so this idea of variance and standard deviation deal with the spread of the distribution. All right, and when we talk about spread or standard deviation, we're going to use some formulas. Now, a little bit about notation first. If I'm looking for the variance, that takes this notation here, which is sigma squared. It's a lowercase sigma, right? This is the uppercase sigma, this is the lowercase sigma, and it's sigma squared. Or we can find it by doing E of the x value minus the mean squared, or we could do x minus the mean squared times the probability. Okay? If we want the standard deviation is just going to be the square root of the variance, and we get it just by doing the square root of what we did above.
Sorry, I couldn't hear.
The easiest way to deal with this, however, is to deal with it in the calculator. And that's what we're going to jump to right here. So I look at this example, still the same magazine example, and I'm going to go straight to the calculator. So I'm going to clear out my screen. I'm going to enter in to L1 my x values, clear, enter, and I'm going to put in these x values in L1. So 1, 2, 3, 4, 5, and in L2 I'm going to put my probabilities. 0.23, 0.38, 0.21, 0.13, and what's that last one there? 0.05. Okay, double check, make sure I entered them right. I did, I'm good. So, how am I going to get that standard deviation and that variance? So, if I go and hit this stat button, which we did in the last chapter, if you remember, and I'm going to go into the calc menu. So, I'm going to cursor to the right. Then I'm going to go one var stats, one variable statistics. Now, my list is L1. Those are where my x values are. My frequency list, I'm going to hit second and then the number 2 to get the frequencies in there. And then I'm just going to hit calculate. Now, this right here, this x bar, that's the same thing as the mean. So the expected number of magazines sold that we talked about a couple minutes ago is 2.36. Down here, this is my standard deviation, 1.09, okay, or actually 1.10 if I round to 3 sig figs. So the standard deviation of x is 1.10. Now they don't ask for it here, but if they did ask for the variance, all I have to do is come in and square that value, and I could do 1.1 squared. I'm losing a little bit of accuracy, but you'll forgive me on that. And I get a variance of 1.21. And these are magazines that we're measuring. Okay? Okay, and finally, talking about properties of ax plus b. So basically what's happening here is that we're multiplying the random variable x times a constant a, and we're adding a constant b to the distribution, and we want to know what's going to happen to them. So specifically, what's going to happen is that if we have some value k times x, we can multiply that k times the expected value of the original value, and that'll give us the new expected value. If we have two random variables here that we're trying to get the expected value of, we can add the two expected values together there. Here, when we're dealing with these formulas here, I can multiply and add with the means. However, with the variance, I don't multiply by a, I multiply by a squared, and adding this b isn't going to change the variance. And you'll notice if I'm looking for the standard deviation, I'm only multiplying by the absolute value of a times the original standard deviation, and again, still not adding. So let's take a look at how that plays a part here. So looking at example 8, we're given a random variable x that has a mean of 8.1 and a standard deviation of 2.37, and we have a new random variable y that's going to have 4 times the original value of x minus 7. So if I'm looking for the mean of y, I can just do 4 times the mean of x minus 7. I could deal with both of those at once. So that's just 4 times 8.1 minus 7. And that is whatever it is. If I'm looking for the standard deviation of y, I'm just going to multiply 4 by the standard deviation of x. I'm not going to subtract the 7 because adding or subtracting doesn't affect standard deviation. So that just becomes 4 times the original standard deviation of 2.37, and that is what it is. All right? So that's it for the first half of this chapter 27. This is the assignment I'd like you guys to work on to get yourselves familiar with these topics. And we'll come back next time and talk about the next part of chapter 27, binomial random variables.